Let's do another example of a proof by induction. Let's say we'd like to prove that 1 plus 2 plus 4 plus dot 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 plus 2 to the n is equal to 2 to the n plus 1 minus 1. So as we add up more powers of 2, we're claiming that this identity holds. Now the first step in any proof by induction is to write down a predicate, say, usually indexed by some variable. I'm calling it n here. So P of n is going to be the statement that 1 plus 2 plus 4 plus 2 to the n equals 2 to the n plus 1 minus 1. It's exactly what we wanted to prove. We'll see some more interesting cases in the future where the predicate that we write down isn't exactly what we want to prove, but in this case, what we'd like to prove is that for all n greater than or equal to 0, P of n is true. Okay, if we can prove that for all n greater than or equal to 0, P of n is true, then we'll have proved that for every n this identity holds. So the first step in any proof by induction is to prove the base case. What's the base case in this setup? Well, it's P of 0, because we want to show that for all n greater than or equal to 0. So 0 is the first case, it's the base case. And what is P of 0? P of 0 says that 2 to the 0 should equal 2 to the 0 plus 1 minus 1. So is it the case that 1 equals 2 minus 1? Yes. So the base case, P of 0, is true. We just substituted in 0 for our predicate here. Now comes usually the more interesting part in any proof by induction. We want to prove that for all n, P of n implies P of n plus 1. And then we'll be done. So this is the statement in quotations we'd like to prove. If we're proving an implication, our first step is to assume P of n is true. Okay, so n is some value. You can think of n as being an arbitrary, some arbitrary large number. And then we want to conclude P of n plus 1 is true. So you could think of P of n as a fact that I've given you that it's true, and I want you to now prove P of n plus 1 is true. Okay, so what is P of n plus 1? It's 1 plus 2 plus 4 plus 2 to the n plus 1 equals 2 to the n plus 2 minus 1. This is what we need to prove. This is P of n plus 1. Okay, so I'm going to rewrite this sum as 1 plus 2 plus 4 plus 2 to the n plus 2 to the n plus 1. Now, I've done nothing here. I've just expanded out the sum a little bit. But notice that this 1 plus 2 plus 4 all the way to 2 to the n, this, because we've assumed that P of n is true, we know that this equals 2 to the n plus 1 minus 1. Okay, these first n terms, when we sum them up, equal 2 to the n plus 1 minus 1. This is often called applying the inductive hypothesis, or the inductive step, because we're applying this P of n, which is our quote-unquote inductive hypothesis. Okay, and now we still have to add on this 2 to the n plus 1 term. So this sum is equal to this. And then look at this expression here. What is this equal to? Well, it's equal to 2 times 2 to the n plus 1 minus 1, and this equals 2 to the n plus 2 minus 1. So we've taken the sum of the first n plus 1 terms, we've shown that they're equal to 2 to the n plus 2 minus 1, but wait, that's exactly what we wanted to prove. That's p of n plus 1. And we did it by assuming that p of n was true in this step right here. That completes the inductive proof. If this is confusing, I suggest you rewind the video a little bit and follow along again.